the last day. Yeah. So okay, so last day we were talking about class sums and their products and so on. And we did say that this will lead to a method for calculating characters, a sure shot method for calculating characters. Well, there seemed to be some debate as to whether it's really worth learning. And the answer is yes and no. Depends on how much group theory you will need, of course. Also, maybe the actual method that is really used is a derivative of the method I'm going to talk about. That's a more advanced method which requires some more math to learn, but it's the one which is really used, because this one that I'm going to talk about today has a few shortcomings in practice. No real shortcomings as far as the theory is concerned, but in practice there are some problems in implementing this one. So there is another method which is actually very, very nice, but uses some advanced number theory. So we are not going to go into that right now, this advanced theory. But the basics of this theory that I'm going to talk about today will be needed even if you don't use the theory ever, the pieces will be needed anyway. So just to remind you what we were doing, we were talking about classes and their products, and we were saying something like this. Let me just give you an example. Our example group S3, which had these elements E, A, B, C, D, F, turned out to have three classes, right? C1, which was E and E alone, C2, which, well, standard notation is the two rotations make up C2, and C3 was the three reflections. Okay? Now, the question was, what is C1, C1? And the answer is, of course, if you think of this as a... Just hold on. Hello? Class है आज urgent? हाँ. সেটা বেস্ট হচ্ছে প্রসূন মণ্ডলকে জিজ্ঞেস করো, হি ইজ দ্য ওয়ান হু উড নো। আমি তোমাকে তার নাম্বার দিয়ে দিচ্ছি। প্রসূন মণ্ডল হচ্ছে কেমিস্ট্রির আমাদের, হি ইজ দ্য ওয়ান হু ইজ ইন চ্যাট। হ্যাঁ, ওর জানা উচিত। এই নাম্বারটা হোয়াটসঅ্যাপ করে দিচ্ছি তোমার। ওকে, না আই ডোন্ট নো দ্য নাম্বার, এগুলো তো আমার জানার কথাও না, জ্যাকের কাছে। প্রসূন মণ্ডল জ্যাকে আছে, ওর বলে দেবে। ওকে ওকে, আই উইল জাস্ট সেন্ড ইট ওভার টু ইউ। ওকে okay, so just hold on, I need to SMS something to our dean. Okay, so I am back, but are you all here?
Yes, sir.
Okay. Of course, the question really meant, am I still here? So this, of course, is just, if you think of this as a standard multiplication of sets, this will be, of course, E, which is C1. Now, things get a bit murkier if you look at C2 square, or C2 times C2, which is dF times dF. We thought of this as a multiplication of sets. Can anybody tell me what the answer should be? Well, D times D is what?
C1 and C3.
C3. Are you sure? D times D is how much? D square. What is D square?
E.
That's, D square is not E. D is a 120 rotation. D square is F, the 240 degree, the 240 degree rotation, right? So D square is F. So there are actually four terms here: D square, F square, which is D, DF and FD, which are both E, right? They're inverses of each other. So if you thought of this as just a set multiplication, the way we had defined it before, then this should really be FDE, which is really, in terms of sets, it will be the union of the set C1 with the set C2, right? That's what we are going to think about. We learned about this before, right? How to multiply two sets together. You just multiply all the elements with each other, and just to realize that after all, sets don't allow repetition. So 2 is the same as the same E, right? However, this is not the version that we are going to talk about today. So when we say C2 square, what we are really doing is something else. What we are really doing is, instead of thinking of C1 as this set, we are really thinking of C1 as the element E1, C2 as the element D plus F, and C3 as the element A plus B plus C. Anybody remember what this is? How come we are adding elements from groups?
Group algebra.
Yeah, the group has a corresponding algebra. So C1, C2, C3 are here. These class sums that we have written down are actually elements of the group algebra. Okay, there's no E1, so that's just C1 equals E. Okay, see. So these are elements of the group algebra, and when we multiply them, we will think of them as elements of the group algebra and then do the multiplication, which of course means C1 square will be E times E, which is E square, which is E. So C1, C2 square. Now D plus F whole square, if you treat it like an algebra, all the standard rules of algebra apply, which means D plus F whole square will be D square plus F square plus what? Plus
DF plus FD.
DF plus FD, of course. This is algebra, it's not necessarily commutative, so we do not put in 2DF. Okay, it's not the twice AB formula, but close. And of course, in this case, DF and FD are both equal to E. But then this becomes F plus D plus twice E, which is 2C1 plus C2. So that's how you do the multiplication. You keep track of the number of times elements occur, simply because you're thinking of this as elements of the algebra. What is critically important here is this, that when you multiply classes in this way, what you're going to get are classes and their linear combinations, even integer combinations. Okay. The proof of this is reasonably simple. I should think it should be pretty easy for you to work this out. But the rule is you will never get half a class. For example, you will never get a situation where you have just have D and not have F. And not only that, you will have D and F exactly equal number of times. So if your multiplication gives you 3 Ds, it will also give you 3 Fs. So it will be 3 times C2 always. If the multiplication gives you that. Here, of course, it's giving you 1 F and 1 D, and E comes twice. Okay. So this is a fact which follows from group properties. It's rather straightforward and simple, but it takes some amount of thought. So I will ask you to think about why this happens for all groups, not necessarily for this one. Here I'm just giving you an explicit calculation for this group, but this thing happens for all groups. If you multiply two classes, you are going to get whole number of classes as a sum of whole number of classes as a result. So we have a few more multiplications to go. C3 square is going to be, okay, what is C3 square? C3 is this one, D, A plus B plus C. So what is C3 square?
C1 plus 2C2 or 3C2.
Well, or and what? Okay, what is this? It's a plus b plus c whole square. What's the standard formula for that? Again, class 8 algebra or maybe 10.
A square plus B square plus AB plus BC. I mean AB BA BC CB CA AC.
AB, BC, CA, BC. Okay. Right. So unfortunately, I'm taking an exam at this moment, so I'm also answering to exam questions. Supplementary. Let's see. Okay, so you just saw the supplementary question. It hardly matters anyway, but still. Okay, you were right. A square plus B square plus C square plus AB plus BC plus CA, CB, etc. So A square plus B square plus C square, that should be what? 3C1, right? A square is E, B square is E, C square is E. And AB, BC is C. So what, there are 6 more terms. What should that be? The 6 more terms?
And there should be 3C2.
There should be 3C2, exactly. Okay, in case you're finding it difficult to figure this out, you should just work it out. Pretty straightforward. Well, we also need C1, C2. And that's easy. C1, C2 has to be C2. C1, C3 has to be C3. So I am aware that my attempt at writing a curly C is looking more and more like an E. But I hope everybody understands what I mean here. Right, C1 being only the identity, this is the only thing that can happen. But C2, C3. Well, what is C2, C3? 6 terms. DA, DB, DC, FA, FB, FC. What should it be?
Two C3.
Yeah, it has to be 2C3. That's sort of pretty easy to figure out. After all, each one of these products is a rotation times a reflection. Has to be a rotation. There are 6 of them. As I said, you will have to have integer number of times the classes occur, which means it has to be 2C3. By the way, I did not work out C2C1, C3C1, and C3C2. C2C1, C3C1 are trivially equal to C2 and C3 respectively. C1 being the identity. But you should be able to figure out the C3C2 is also the same as C2C3. Well, of course, it's obviously the same by direct multiplication in this case. However, I will urge you to think about this in general. Class multiplication is commutative even though the original group may not be abelian. That's always the case. Again, figure out why. Okay? Simple group theory. There's nothing very difficult about it. Simple group theory ensures that that will happen. Okay? So now that we have the examples here, by the way, you should realize that I have not given any proofs for this. All I have done is I've given you an example. That is for our standard example that we have been using so far, the group S3 or symmetries of the equilateral triangle. I do get products like this. Okay? But in general, this is a statement I'm going to make. That if you take classes for any group, take the ith class and the jth class and multiply them together. When you say ith class and the jth class, you mean as elements of the group algebra. So the class is really sum of all the elements belonging to the class. If you do that, what you're going to get Now, here I have another problem. I have to write the number of classes. I've unfortunately used NC before to indicate the number of elements in the class C. Here I mean curly NC, which is total number of classes, which I should have actually put in notation for before. Okay, this is what comes out, where HIJKs are all integers, in fact positive integers, or non-negative integers to be more precise, of course. Okay, so this is a class algebra for any group. For any finite group, you on the class algebra. Of course, for large groups, it may take some more effort to write this down, but you can write down the class algebra anyway. Pretty straightforward. Okay, and these integers define what the class algebra really is like. Okay, now here comes this. Okay, and we also managed to define something called HI, the ith class coefficient matrix, whose jkth element is simply this HIJK. Okay, so action, you can now sort of think of it like this, that acting by Ci on the class Cj is sort of like the matrix Hi acting on a vector, on a nc dimensional vector with coefficients C1, C2, C3 down Cn. Can you see what this is doing? If you took Ci and then put all these classes C1, C2, Cnk in a column vector, in an nk dimensional column vector, you would really getting this Hi acting on the same matrix, right? Is that okay? So multiplication by Ci sort of looks like the matrix Hi acting on this. So in our example, we have three, of course, we have three classes, so we have three H's, one for every class. H1 is what happens when C1 acts, right? So what does C1 do? Just to remind you, okay, let me just write ordinary C's. I'm getting tired of trying to write curly C's, which look more and more like E's. C1, of course, is C1, C1, C2 is C2, C1, C3 is C3. Okay, so what will H1 be? Take the vector C1, C2, C3, act upon that by some matrix which will give you the right hand side. And of course, the matrix here is rather trivially 1, 0, 0, 0, 1, 0, 0, 1. Okay. What about H2? You will take C2 and apply that on C1, that you get C2. C2 apply that on C3. What will you get? We had worked it out before. So C2, C3 is simply 2C3. Okay, we also need to, we forgot this C2C. Okay, let me just. So C2 then goes and acts on C2. That's C2 square. That, remember, is 2C1 plus C2. So let's put that in. And C2, C3 is simply 2C3. So what does this matrix look like? This matrix looks like 0, 1, 0. That's 0, C2, 0. 2, 1, 0, 0, 0, 2. By the way, there is no transposition, which, hold on, sorry. Hello. About. Okay, so I'm back. And with this comes the last one, H3. So I hope everybody realizes that I'm using this matrix representation in a standard one sense, right? It's JKCK. If you remember the sum, this is actually, okay, HI's JKCK. So it's like coefficients are being acted upon by a matrix, not the basis vectors. So there's a column to row transposition that people do that you don't have to do here. Okay, finally going back to C3, C3, C1 is obviously C3. So C3, C2. Well, we have already written that down as 2C3 and C3, C3. C3 square is 3C1 plus 3C2. So here the matrix will be 0, 0, 1, 0, 2, 0. Sorry. Oops. Three, 0. Okay, so these class coefficient matrices are going to play an important role in what we are going to do next. Now, by the way, this part is something which is important to know, even if you don't want to use the special method for calculating characters, simply because this is going to come in handy in many applications later on as well. So the way class, after all, remember the characters are ultimately class functions, and many things about group representations essentially depend on the classes and not so much on the group elements. And these properties of the classes come in handy over and over again. Okay, but now let us talk about a specific thing which is of interest for representations in particular. So far, whatever we have said has nothing to do with specific representations. So far, whatever we have said is true for group in general, and this is just all so far is basically abstract algebra. Now we come to specific representation issues, and for that, and that is why I was trying so hard to write curly C's so far, simply because capital C's are actually the representation that we use. So for the ith class, Ci is simply defined this way. For a particular, say we have a representation D, which means for every group element, there's a matrix DG. So the class matrix, which is what capital Ci stands for, take the ith class, take every group element which belongs to the ith class, take the representation matrices, simply add them together. That's it. That's the ith class matrix for a particular representation. Everybody with me so far? D is any representation, so every group element has a corresponding matrix. You just add up the matrices corresponding to elements belonging to the same class. That's how you get the class matrix. Is it okay?
Sir?
Yeah.
Can we say that the linear combination of all the classes is a subalgebra of the group algebra?
Well, actually, you can do more. It's like a subalgebra of a very specific kind.
And commutative subal.
It's called not only commutative, the combinations are only integers. So it's a technically slightly different. It's actually technically a lattice. We don't really want to go into that.
Okay.
It's a more specific kind of thing. Just integer combination. Just remember lattices that you studied in crystals. Basically the same kind of thing. Not exactly the same kind of thing. It's basically only positive coefficients. So it's a restricted version of that.
And the matrices H, can we think of them being applied on that algebra?
Yeah, actually that's exactly what we are doing. Right? That exactly is what we are really doing. Okay, but right now we are going to think of something simpler, because notice that class algebra was rather abstract, right? Because we had this group elements where the sum was just a formal sum. We did not know how to add up A and B and C really. We just said, okay, let's define A plus B plus C to be an element. And then go ahead and do all algebra with it, assuming all the laws of algebra stay intact. That's all we did, right? That's how we introduced the group algebra in the first place. However, for representations, you should realize that what we are using are matrices, right? We know how to add matrices. Okay. So dj is just a sum of simple, suppose D is some n by n representation. DGs are all n by n matrices, we're just adding them together. It's just a sum of matrices, right? Much simpler. And now, what will immediately happen, that this result that we wrote down, we must hold for class matrices as well. Do you realize that? Because all we did when we dealt with the class combination rule, we're using abstract algebra rules for the group, but now we have a representation of those group elements by matrices, and this algebra that we did to calculate, say, say C2 square, that algebra of course still works here just as well, right? Does everybody get that? So, for example, in my particular case, C1 will be just D of E, which will of course be the identity matrix, n by n identity matrix. C2 will be D of D plus D of F, another n by n matrix. C3 will be D of A plus D of B plus D of C. Okay. But when you say multiply C2 with C3, what will happen? You're going to get D of D into D of A, that's D of DA, because we are dealing with representations. So D of DA is one of those AB, either B or C, so it's going to be DB and so on. It's pretty easy to see that whatever we did for the abstract group algebra will work perfectly well for the group matrices, right? That alone is not that great. What is important is this. Suppose I took this D inverse G, and then we took my class matrix for the ith class. This is a trick which we have played several times before, right? But earlier we had played a trick for where the thing sitting here was a sum over every group element. Here that's not the case. Here, what is sitting here is a sum over all group elements belonging to a particular class. And this, of course, will still go through. Take all the group elements belonging to the ith class, and then D of D inverse GI. But can anybody tell me what this is going to be, this sum? You have seen this argument used at least twice before, if not more. Once when we dealt with unitary, with the fact that every finite group has unitary representations. Again, when we just use Schu's lemma to get those orthogonality theorems, right? We use this fact that the sum over every group element is invariant under this kind of unit transformation. But can anybody tell me what will be the case here? I'm not summing up over the entire group. I'm summing up over just a class, the ith class.
CI.
This will also be CI. Okay, is everybody clear about that? Yes? No? Maybe? What? So I'm assuming everybody understood this clearly. Okay, so let's move on. If everybody has understood this, then the next step should come in. Oh, okay, what should be the next step? Tell me that. What does this really tell you? This tells you the CI DG is CI, is DG CI, right? For all group elements belonging to capital G, this is what works. So what, if anything, does this tell you about CI? Yeah, tell me. CI is a matrix which commutes with every matrix of a representation DG.
From Schu's second lemma, I don't remember the exact result, but it should be some identity.
You mean multiple of an identity? That's what the Schutz second lemma says.
Yes.
No. That's not really right. Close, but not right. Can anybody tell me what's wrong with that statement? Does anybody remember Schutz second lemma? That's actually, yeah.
It's true if D is an irreducible representation.
Exactly. The point is this statement that we made so far is true for every representation. Okay. Now, if D is an irrep, now that's really where you were going. If D is an irrep, now I find that the matrix Ci alpha, say D is an irrep, let's say D alpha, then we have a Ci corresponding to that irrep. That is, of course, matrices corresponding to that irrep, you add them together, you get class matrices corresponding to that irrep. And Ci alpha commutes with every element of every matrix element for corresponding to an irreducible representation. So Ci alpha must be a multiple of the identity. Of course, a d alpha dimensional identity. That is, if the dimensionality of the representation is small d alpha, the identity, of course, has to be a d alpha by d alpha matrix times an eigenvalue, a constant number. Not an, okay, let's not call it an eigenvalue, although I have written lambda specifically because it looks like an eigenvalue. Notice that every one of the class matrices have to be multiples of the identity. Of course, which multiple, that will depend on two things: which irrep you are talking about and which class you are talking about. So in our example, we have 3 classes, so there will be 3 lambdas for every irrep. Okay? But how is that relevant to us? These lambdas, can you tell me how they are related to the characters? Remember, the character, of course, depends on the class. So I can just use the I index. I means for every element belonging to the class Ci. Can you tell me how these lambdas are related to the characters? Just to remind you, this is what Ci alpha really is. And Schur's lemma has just told us that it must be a multiple of the identity.
Lambda I alpha.
Lambda I alpha d alpha is, okay. Anybody with a difference of opinion? Could you explain why you are saying lambda I alpha d alpha?
It is a trace of the representation matrices, right?
Yes. Okay. So the right hand side of this expression has a trace, which is of course lambda I alpha d alpha. You're right about that. Lambda I alpha is just a number. It's a multiplying number, and identity of course has a trace of d alpha. So you have lambda I alpha d alpha. Right. But then
There, there should be an NCI somewhere. It
where?
should be by NCI lambda I alpha d alpha by NCI equal to chi I alpha.
This is what you're saying.
Yes.
Okay. Can you explain that?
Because Ci alphas are summation over I d alpha g, and since g belongs to Ci, and if you take the characters, so the individual characters are actually chi I alphas. So
Exactly. So actually, when you take the trace of Ci alpha, you are actually taking the sum of the traces of every one of the representation matrices which go in for the class Ci. And since there are NCI of such matrices, each one of them have the same character. Remember, character is a class function. It depends only on the class. So it's the left-hand side really is NCI times chi I alpha. The right-hand side, as was correctly said, is lambda I alpha d alpha. But you have to divide by NCI. So notice that if I manage to find the lambda I alphas, I'm actually done. I actually know the chi I alphas, right? So this finding out the characters, that job essentially boils down to finding out the class matrix, the lambda I alphas corresponding to class matrices. Okay. So this might even give you a sort of way of checking whether a representation is, if you are given a representation, that is, if you are given all the matrices corresponding to a representation, it might very well happen. There are many situations where the matrices come out naturally from a calculation. Then you should realize that one way of checking this, whether this representation is reducible or not, although it takes a bit more work than the standard way, is simply find out all the class matrices just by adding together the matrices that are given to you. Take the matrices belonging to a particular class, just add them together. If you get multiples of the identity, you are done. Remember, the individual matrices may very well be very different. Apart from the matrix corresponding to the identity representation, which of course has to be identity, or the identity element, which has to be the identity, other matrices may be pretty non-trivial matrices. But when you add them all together for a given class, you should get a multiple of the identity if you are dealing with an irrep. So if you get a multiple of the identity, fine, you've got irreps. Done. Okay. And what multiple? Those are the values of lambda I. And since you know lambda I, you know d alpha, because since you are given the matrices, you know the dimensions. Then finding the character simply becomes just take the lambda I, multiply by d alpha, divide by the number of elements in a class, you're done. Okay. Right? So if you're given a bunch of matrices, checking whether they form an irrep, and if they do, finding out the characters corresponding to that irrep becomes a trivial task. Okay? Everybody with me so far? Yes or no?
Yes, sir.
Okay, but now comes the real question. The real question is, if I'm given all this hinges on being given a representation and then going ahead with it. Of course, the representation that's given to me may not be an irrep, in which case I don't get a multiple of the identity, I don't get the lambda, then it doesn't really help me in any way. Okay. So the real question that I have is, can we actually find out these lambdas and even the d's from just the just the basic group algebra, nothing to do with any particular representation, just look at the group algebra, will that tell us what is going to be the case? The answer lies in the H matrices that I had written down a while ago. Okay?
Sir,
Yeah.
I couldn't hear what you said. Can you repeat?
No, what I said was if you are given a representation, then this gives us a pretty easy way of checking whether it's an irrep or not. And if it happens to be an irrep, if you're lucky enough to get an irrep, then you're done. Then that irrep will tell you this what do you call it? Then this irrep will tell you what the lambdas are. Okay, and these are, of course, if it's an irrep, its dimensionality gives you the d alpha. The C alphas are going to see. How do you know it's an irrep? Because Ci alphas are going to be multiples of the identity. And you get lambda I alpha, D alpha, NCI is, of course, a property of the group. And you get the chi I alpha, all the characters corresponding to that particular irrep. Of course, the downside here, of course, is that, first of all, you need to find an irrep somehow. So you may try representation after representation and then might just hit on an irrep. Okay. And also, this will only give you results for that particular irrep. So if a particular group, like this one has 3 classes, I manage to find one irrep, it will just give me information about that one particular character, row of the character table. The question is, can I find out the character table or all the characters and even the D alphas just from the group algebra? Now, we have already done that, by the way. For this particular group, we have already found out the entire character table. We have found out all the group, all the dimensionalities, how many classes there are, what the dimensions are, everything, right? But let's just pretend we haven't done any of that. We don't know anything. We just know these class equations. And can they be enough to give us the characters? And not only the characters, can they also give us the dimensions of the representation? Now, you might say that's a bit of a stupid thing to do because, after all, for this particular group, I know the dimensions pretty easily. It's just 1 square plus 1 square plus 2 square has to be 6 and so on. But remember, that's true because we have a pretty small group that we are dealing with here. What I'm describing will work for every group and is something which you can automate. You can put it on a computer and the computer will automatically do the calculation for you. So give the group structure, the computer can automatically calculate all the characters. And that's essentially how it is done in nowadays for large groups, even immense groups. It's just a matter of spending some amount of computer time. So the aim now is, given just the class multiplication rules, which essentially means just these facts, just this. Okay, how do the classes multiply? Or basically, which is effectively the same thing, just find just these 3 matrices, H1, H2, and H3. Can I use these to find out the characters? And the character tables and the rest of information about the representation. Okay, and the answer lies in this. Remember, I just said if you take the ith matrix capital HI and now I can actually safely write capital C's and not curly C's, because here I'm not saying that HI is acting on the classes. Here I'm saying HI is acting on the matrices. What am I supposed to get? I'm supposed to get lambda I. Everybody with me so far? Or have I lost you here? Okay, sorry. This is not true in general. This is true for irreps. By the way, in case you are not following this, let me just write this down for you. Ci, Cj, remember, is sum over k going from 1 to nk, number of classes, Hij, Jk, Ek. That's the general rule for class matrices. Of course, this also works for. Okay, let me just forget about this. This is a much simpler way of writing this, so we will do that now. Okay, so this is the class relationship, right? It was a relationship between classes, but now it's a relationship between class matrices. It was a relationship for arbitrary representations, but now we are talking specializing to irreducible representations. In which case, this type simply becomes lambda I alpha, right? We know that for the irreps, the class matrix is just multiples of the identity. We just use that. What that means is this part must equal this part, right? Is everybody clear about that? And now, just think
Yes.
of this as Hi, the matrix, whose jkth element is Hij, acting on lambda alpha 1, lambda alpha 2. Okay, and that's equal to what? What is the right hand side? Forget the identity. After all, if these are two are multiples of the identity, so the multiples had better be the same. The left hand side essentially means gives you this. Actually, I'm writing this is the jth element of this particular equation that we are writing down. It's just going to be this. You get that? That's exactly what this relationship is, right? If you think of this lambda I alpha, for the time being, just think of this lambda I alpha is as a number. It is, of course, all the lambdas are numbers, but think of this as basically the jth row of a big column matrix, and that's exactly what this equation tells you. The jth row of this matrix equation will be exactly this one. Any questions about this? Yes? So if there are no questions about this, I'm not sure whether this was completely unintelligible or it was so obvious that there's no point in really talking about it. But what does this really say? It says that I have three, in this case three, because we have three classes. We have three class coefficient matrices H1, H2, H3. And basically, our lambda I alphas are nothing but the eigenvalues of that particular class quotient, of the class quotient matrices. Right? Is it okay?
Yes.
Now, here we have three class coefficient matrices. So the job essentially becomes find out the eigenvalues and eigenvectors of these three matrices. But it's actually simpler than that. Because if you realize, the eigenvalue here, of course, depends on I, right? Which particular matrix you're put in. But look at the eigenvector. Does it depend on Hi? Does it depend on I? Of course, it depends on Hi. But does it depend on whether it's H1 or H2 or H3?
No, it
It
doesn't.
doesn't, right? So what does this tell you about the three matrices H1, H2, H3?
They have a common eigenvector.
Yeah, they're not a common eigenvector. They have a complete set of common eigenvectors. Actually, they're simultaneously diagonalizable. What that makes it very, very easy, because it's easy to diagonalize one of the matrices. And if you manage it, and you manage to do it without degeneracy, that's even better. Then you have actually found out a complete set of eigenvectors for every one of the three matrices. Right? So you don't really have to worry about doing it separately for all three. Do one, but choose that one wisely, in the sense that if you try to find out the common eigenvectors for this, what will you get? What are the eigenvalues of eigenvectors for H1? Yes?
Any vector.
Yeah, eigenvalue is 1. There's only one. This is a threefold degenerate eigenvalue. 1, 1, 1. And eigenvectors are, any vector would be an eigenvector. So it really doesn't help in simultaneously diagonalizing the other two. You will find H2 also has a degeneracy, but H3 does not. If you work out the eigenvectors and eigenvalues of H3, that gives you the eigenvectors and eigenvalues for all three together. They're called simultaneous eigenvectors, and you can find out all the characters without any work whatsoever. Okay. So this is basically the idea behind what is called Burnside's method. Simply start from the basic group algebra, that is, you know how the group elements multiply among each other. Identify the classes. Once you've identified the classes, by the way, that you have to do anyway for anything to do with representation. So there's not extra work. You have to identify classes anyway. The only extra piece of work that you're doing is you are trying to find out how the classes multiply. That is, if you take algebra elements corresponding to classes, class sums, how do they multiply? That is, find out the matrices HI. And once you have found out the matrices HI, diagonalize one of them. If that happens to be degenerate, then even then you get some information. Use that to diagonalize the other. But if you're lucky, you can hit upon one which is already non-degenerate, which gives you all the eigenvalues and eigenvectors in one go. So all the lambdas are done. Okay, I will just leave you with one homework, since I'm not taking a class this Thursday, so we are only going to meet Tuesday. Now this is going to be, this is going to be graded. Okay. So I will ask you to
I have
read up.
some doubt.
Yeah, go ahead.
The H1 matrix for any group, this one H will be identity, right? I mean,
Right.
so I mean, the method tells us that any diagonalizing any matrix will give us the result. I mean, if we diagonalize just H1, we will have
No,
all
it
the.
doesn't tell you that diagonalizing any matrix will give you the method. It tells you that all three matrices are simultaneously diagonalizable. Okay. So you have to simultaneously diagonalize all three matrices. All I am saying is, if the matrix which you happen to diagonalize happen to have non-degenerate eigenvectors or non-degenerate eigenvalues, then you are lucky in the sense that you don't have to do any further work. That particular choice of eigenvectors will definitely be eigenvectors for all the three matrices or all the MC matrices in general, number of classes. Okay. But if in turn, for example, if you started with H1, that would be rather stupid, because H1 tells you one correct piece of information, which is one of the characters is 1, or one of the lambdas is 1, but that's obvious because that's what you get for the identity representation, which is always a representation. But it does not give you any further information beyond that. It does not tell you, pinpoint in any way, which particular eigenvectors you are dealing with. Okay. After all,
So, if H1 is applied to any vector, it will give the same vector.
Right. So every vector is an eigenvector. Right. That's what it means to say it's threefold degenerate in this case.
And
It has a
the
threefold. The eigenvalues are one always.
one. So okay, I've got the answer. I was thinking the eigenvalues will.
No, the eigenvalues. Look, all you have found out is that HIs have eigenvalues which are those lambda values, right? That you know. Okay,
We'll only get one of the
but it's
lambdas
not
from.
necessary that you will get all the lambdas from one matrix. Of course, you will. If you tried H3 in this case, you will find all three. You get three distinct eigenvalues, which actually tells you that you have got all the three eigenvalues, all the three lambdas at one go.
Okay, I've got.
By the way, how many lambdas do you have? Do you have three or more? In this case,
3.
no. You actually have 9. Lambda alpha I. Remember, lambdas depend on the representation and which class it belongs to. Okay, so even finding out the three eigenvalues is not that great. H3 has three eigenvalues, three distinct eigenvalues, but that's really not what I'm really after. The three eigenvectors. Remember, what are the eigenvectors of HI? Let's look at the eigenvectors. The eigenvectors are also vectors where lambdas are sitting, right? The three eigenvectors that you get, three independent eigenvectors that you get for H3, they will in one go give you all the characters without any other work. Those are the 9. That is where the 9 elements are. So I'm leaving this for you to work out and think about. Okay. There will be 9 elements which you will get from the diagonal. Essentially, the diagonalize. Remember, if you put in all the eigenvectors together, one after the other, what do you get? You get a diagonalizing matrix, right? It's a diagonalizing matrix which really tells you what all the characters are. So I will ask you all to read up Burnside's method. There are problems with this method. There are problems with numerical instabilities which might sometimes happen if you try to put this on a computer. There is an improvement called Dixon's method, which is actually what is used almost everywhere. Because Dixon's method has the advantage that it only somehow boils this problem down to finding out integers. Now, remember one thing. Finding out floating point numbers accurately using a computer is always a problem because computers can't distinguish between very close floating point numbers, and whenever you have, say, subtractions of very close numbers, you may very well end up with a huge error. But if you have an algorithm where you're dealing only with integers, then the great thing is the integers are something which you can easily calculate without error, right? Because each integer is separate from the next integer by a large margin. So Dixon's method actually is based on this particular method. It adds some nifty number theory to it to essentially ensure that you get an algorithm which is guaranteed to be error-free of this kind. Of course, you may mess up if you are doing it by hand and replace a 2 by a 3, but a computer will never do that. But a computer can very well mistake a 2.110 with a 2.111 depending on its precision. So Burnside's method has some issues. Dixon's method is the actual method which is used in computers nowadays. I'm not going to discuss that. That's the part which you can, if you are interested, you can always read up. It's available on the net and in different books. But what I'm asking you to do as homework, as holiday homework, let's say, is this. Apply Burnside's method to find out the character table for S3 and also the character table for all symmetry elements for a square. I have deliberately left out some pieces of Burnside's method, something. For example, I've not told you how to find out d alpha from here. You should be able to figure that out pretty easily. Of course, you might say that I already know what the d alphas are. I know what the dimensions of the irreps are, but I'm not going to allow you to do that. Just from this group algebra, class algebra, you should be able to find out everything. Now, while you may not actually need to use Burnside's method or Dixon's method for your actual work ever, for the simple reason that if you ever needed a character table for a complicated group, almost certainly is there in a book, and you can read up the book, or you can just look up a table. But the ideas which go inside Burnside's method actually are quite useful, and they're used in many different places. So we are going to definitely need to understand these basic ideas. So everybody clear about the homework? And what I need you to do is submit this to me by, okay, what's the reasonable deadline? Tell me. Is 1 week okay, or do you need a bit more time? So this is the homework. Use Burnside's you will find Burnside's method in many places, net and everywhere, but I've already given you whatever you need today. Okay, so deadline. I need you to mail me your response by when? Is the next Tuesday too early or too late? I'm sure nobody will say too late, but is it too early? Okay, maybe next Thursday. So I'm assuming from this thundering silence that everybody agrees with this, right? Okay, today I don't have much time left because I have to jump into a meeting after this. Next day, we are going to start properly with molecular vibrations. And there's one more piece of basic representation theory that we have not done so far, which is projection operators. But I will do that while we are actually calculating things with molecular vibration. So this is what we need to still talk about, how to basically give it a representation, how to take out the pieces which belong to a particular irrep. Just like I said in the last day, we can identify that some things are translations, some things are rotations, but which ones are actually translations or rotations? Or which particular, which particular modes of operation, modes of vibration correspond to which irrep? But let me just point out that this was our basic theme. That did we, by the way, remind me, did we do this for a squarene or a trianguline? Did we do it for a?
We did it for a squarene.
Okay, we did it for squarene. So okay, next day we are going to be more adventurous, and we are going to do it for an equilateral triangle, a triangular molecule, which is actually more realistic than a squarene anyway, or more common. What we are going to do is we are going to.
So wouldn't a triangle be easier than a squarene because it has less number of vertices and all?
Well, actually, the representation matrices are more complicated because of all these cos 60, sin 60 which comes in. So it's really not true that a trianguline will be easier than a squarene. It is easier in the sense that ultimately you have less number of things to worry about. But you go into the actual details and trying to find out what the actual coefficients are, you get much more complicated things. Now, first of all, let me just illustrate that for the trianguline, we have, again, let's stick to 2 dimensions. So every atom can move in 2 dimensions. So we can talk about the atomic displacements in terms of 2 vectors, right? Now, the vectors, basis vectors, how do we choose them? There's one choice which I put in. This is for the molecule on top, atom on top, a horizontal and a vertical line. What about a molecule here? Or the atom here? What kind of basis vectors would I use to describe its movement? Of course, I need 2 basis vectors. And then what's the next thing that you would do? How would you put them? Well, for want of any better idea, what we can always do is just go like this. That is, right? But why did I say for want of a better idea? You should realize that all I've done is just taken the simplest possible thing, take parallel axis for all of them. No thought involved really. And then the downside is that the matrices that you'll get, I'll get of course 6 by 6 matrices to describe molecular motion. These 6 by 6 matrices will not really be very easy, not all of them. At least, okay, this one will be easy. Say, identity will always be easy. Identity means do nothing. All the 6 basis vectors stay the same. You get the identity matrix. Now this dA, can you quickly give me all the 6 coefficients? As a 6 by 6 matrix, and write that down. What does dA do to E1? What does A do to E1?
-1.
So it will be -1 here and then zeros down the line, right? 1, 2, 3, 4, 5. 5 zeros. That's easy. What about E2?
1.
Well, E2 is not 1, it's 0, 1. What about E3? What happens to E3 when you apply A?
All remaining 4 will be zeros.
You mean all 4 will be zeros down the entire column will be 0?
Yes, sir.
No, I think you're confusing with the characters. I'm writing the matrix. I'm asking what happens to E3 when you reflect. You're definitely not suggesting that E3 vanishes when you reflect, right?
Minus E5.
So E3 becomes minus E5, right? So this will become 0, 0, 0, 0, -1, 0, right? What about E4? E4 will become?
E6.
That's similarly E5 will of course become minus E3. So 0, 0, -1. And E6 will become E4. So 0, 0, 0, 1, 0, 0. This matrix is not that bad. It's not very difficult. Okay. And now, reflection in this light. Now that is going to be a lot more difficult to write down. Okay, it's not very difficult. Come on, it's basically kid stuff. But still, the matrix will not look so nice. Right? You get that it will not look so nice, right? After all, what will happen to E1 when you reflect? To understand it better, just imagine a vector parallel to E1 but going through this point. What will happen to that? How much angle does that make with this line of reflection? What is this angle?
30.
30 degrees or pi by 6, right? So this vector, when you reflect, it will become like this, making an angle of 60 degrees with the horizontal, right? 30 degrees with the line on the other side, so that's 60 degrees with the horizontal, right? So can anybody tell me what E1 will become under A? Oh, sorry, not under A, this was under B.
Half E5 plus root 3 by 2 E6.
Right. I hope everybody gets that. First of all, the atom at this vertex will of course go to this vertex under the reflection. So whatever displacement you had for this essentially becomes a displacement for this after reflection. So it will be expressed in terms of E5 and E6. And the angles are 60 degrees and 30 degrees respectively with the 5 and 6 axis, which means cos 60 and cos 30. Half and root 3 by 2 will be the coefficients. Okay. So if you write down the matrix, this will have matrices with more complicated looking elements. Smaller matrix, of course, a 6 by 6 matrix as opposed to an 8 by 8 matrix there. But there, the 8 by 8 matrix was rather easy to write down. Here, the 6 by 6 matrix is not that easy to write down. Still, not that bad. And by the way, the characters are, of course, easy. If you all you ever needed were the characters and nothing else, then the calculation would be equal. It would be quite easy. Okay, what about the character for identity? Could you just tell me quickly what the characters will be? Chi for the identity will be?
Six.
That's the easy part. Now, chi for BC, I don't even worry about that. Just tell me chi for A, because chi B, chi C are the same.
0.
Right? You can see it's 0 because the matrix is written down for you. But even if it were not, remember that as far as A is concerned, this atom and this atom are not going to contribute to the character, right? They are being swapped. So E3 has, after applying A on it, E3 will have no E3 in it. It will have E6 or E5 possibly, but no A, no E3. Similarly, E4, same thing about E5 and E6. So only atom which you have to focus on is the top atom, because that doesn't move when you reflect. But that, of course, gives you a trace of -1 + 1, 0. So even if I had not worked out the matrix, I could have written down 0 very easily. And chi D, I don't even bother with B and F because they have to be the same. And what about chi D? DF, right? Chi D, chi F. These are the two. What does chi D have to be? Has to be 0 because rotation through 120 moves all the vectors. So I don't even care what the matrix looks like. There can be no diagonal elements in that matrix. All the diagonal elements have to be 0, which means chi D, chi F are also 0. So this again is rather unsurprisingly, again very similar to what we had before the squarene. This is the regular representation for S3 now, right? And we know that this representation has two one-dimensional representations once each, and one two-dimensional representation twice, right? And then we can just follow whatever we did for the squarene, figure out which ones were other translations, which ones are the rotation, and drop them, and you're left with the other matrices. Okay, having said that, okay, if we never needed if all I needed to know is what kind of irreps you have, and hence what kind of degeneracies there may be in the vibrations, but nothing further. I did not even need to know what the rotations were like and so on. What these independent modes of vibration look like and so on, then just the characters would be enough, so you don't even have to bother about the matrices. But actually, if you really want full information about the molecular vibrations, then just the characters is not enough. You also will need the projection operators, which will tell you what the modes will look like. For that, you need the d alphas. Okay? It's really not so characters will tell you a lot about what's going on, but they cannot tell you everything about what's going on. So, despite the fact that characters are easy to deal with, hardly any work, sometimes you have to get your hands dirty and actually deal with the representation matrices. So, this is not a homework, but before next Tuesday, write down all the 6 D matrices for the 6 elements, because we will need them to understand the molecular vibration of a triangulene molecule. Okay. So over the next couple of classes, we will do 2 things. We will deal with so we will deal with the vibrations of a triangulene molecule, and then we will deal with what happens with the triangulene. Instead of being dealing with the triangulene where all 3 are identical, we will deal with a molecule like AB2. So in isoscalia, say, and that actually becomes a very important issue of what happens when you do isotope substitution on a molecule, and how you can help. Well, of course, AB2 has lower symmetry than an isosceles triangle, and it might very well be that instead of using 3 identical atoms, you're substituting one with a different isotope. So same chemical properties, but different symmetry, so will lead to some differences in physical properties. Sometimes quite substantial differences in physical properties. So we will see what group theory says about that over the next couple of classes. That's next week. Okay. So today I have to quit because I have to attend the meeting now. Anyway, I hope everybody is clear about the homework and what you're supposed to do before the next class. So any questions?